Let's go with the fractional knapsack problem first. That was actually problem 2 for today, but I found that it was easier and it helped in understanding the other problem. So let's start with that. So let's go through the problem statement. We have been given weights and values of n items. You are also given a knapsack of size W. Your task is to put the items in the knapsack such that the total value of items is maximum. So of course, in problems like this, if you have solved yesterday's problems, seen yesterday's problems, we'll use the greedy approach. What is the greedy approach for people who are not familiar? It's an approach in which we take the most optimal solution at this position without worrying about the later consequences. We assume that it is correct to take the highest value at this interval of time, and it will eventually doing that will lead us to a correct answer. So this problem, let me just give like an example for you all to understand. Suppose a bank robber is robbing a bank, of course, a bank vault, and he can only carry out 50 kilograms of stuff back out with him to escape without getting caught. If he carries more, he'll get caught, so he doesn't want to do that. And inside the bank vault, there's 1 kg of diamonds, 100 kg of gold, and 10,000 kg of silver. What do you think the thief will steal? Like he has only 500 kg of capacity. What will he go on stealing? Do you think the thief will take the silver first or the gold, or what will he do? What approach will the thief follow? Of course, the thief
Diamond,
will. Hmm?
diamond,
Yeah, of course, he'll take the diamond first, right? Why does he take the diamond first? What is his reasoning behind taking in the diamond? Why will he steal the diamond?
because he wants to steal the maximum amount of the stuff in amount
Exactly.
terms
It's
because it is
most
precious
valuable.
diamond.
Yeah, diamond per kilo is worth more than gold or silver, right? So he'll take that first. He's not concerned that by taking this 1 kilo of diamond, I'll be able to take one less kilo of gold or silver, because that 1 kilo of diamond is worth more, right? So he's being greedy and he is taking what is worth the most. So he'll take that 1 kilo of diamond. Now he has 49 kilos of space left. So what does he do? He can now choose only from gold and silver. There's only 1 kilo of diamond, right? So now he'll follow the same approach between gold and silver. What is worth more per kilo? It is of course gold. So he'll pick up the 49 kgs of gold and he'll ignore all the silver and move around. And if you see, if you come up with any combination of gold, silver, and diamond, this will be the most optimal solution, right? He can't get away with more than this, correct? So, what was his approach? His approach is basically finding the most valuable stuff per kilogram and taking that. And this is possible because we are allowed to break the items. Suppose if it was a massive gold block and the thief could not break the items, it would be a different story. But here we are imagining that he can take as much as he wants. He can break items in half, in one fourth, take whatever fraction of items he wants. So we've understood the approach, right? Take something that has first we need to sort it in order of highest value to lowest value per kilogram, and then go in order and take items until our backpack is full. Maybe if you'll understand better through a numerical example, then n equals to 3, that means we have 3 items. W equals to 50, that means the capacity of the backpack is 50, and our values are 100, 60, and 120, and the corresponding weights are 20, 10, and 30. So first you have to determine which is most valuable per kilogram, right? For item 1, the value per weight is 100 divided by 20, that is 5. For item 2, it is 6. And for item 3, it is 4. So, of course, what is most valuable? Item 2. So, we'll take as much as we can of item 2. How much of item 2 is present? Only 10 kilos. So, we'll take all 10 kilos because a bag can accommodate 50 still. So, taking that 10 kilos is the best thing we can do right now. So, we'll take that 10 kilos. Over here, initially capacity, remaining capacity is 50 and we have zero value. we have item 1 of weight 10 which we can pick up. So actually this should be item 2. Item 2 this should be over here. Item 1 they said because the first item we are picking up, but item 2, that is the value of 60 that we are picking up, and the remaining weight is 40, right? We picked up 10 kilos, our value became 60. Now we do the same thing for 40. What is the next most valuable? 6 is completely exhausted, we can't take 6 anymore, so we'll see 5 and 4. 5 can be taken, correct? So we will take 5. 20 kilos of 5 is being taken. Our value is now 60 plus 100, 160. And our remaining space is what now? Our remaining space is 20. We've taken 10 initially, then 20 more, and our initial capacity was 50. So we have 20 more to go. The last item, this is the only one we can take, but notice it has a weight of 30. We can't take the full item. So we'll take 20 and the 20 kilos of that. What is the value per unit weight? It is 4. So 20 kilos will have value of 80. So we add 80 to our value, and our total value is 100 plus 60 plus 80, that is 240. So that is the approach for this problem. Very, very simple. As you might have noticed from yesterday's problem, this problem also, greedy approach most of the time is just sorting in the desired fashion and then picking up things greedily. The algorithm is self-describing, right? Be as greedy as possible and you'll get the right answer. Comes very naturally, and that makes it a very easy problem. Before I discuss the implementation, does anyone have any doubts on like the approach, intuition? Okay, so then I'll move on to the code. Code does exactly what I've described. The thing you might be new to in like C++, notice I said we need to sort by weight, value per unit weight, right? But in what form are we given the items? We are given a vector which has a pair of integers inside. It is a vector of pair of integers, and the pair are weight value pairs. So pair ka first item is weight, second item is value, and now I need to sort this. I can't use sort directly, right? Sort items dot begin items dot end. If I do that, it'll sort it in the descending order of weight, which is not what I want. I want descending order of value divided by weight. So for that, I can use a custom comparator. A custom comparator is a function which returns a boolean that is either true or false. So I have to pass it in two parameters, that is two elements of my vector. Suppose A and B, I have named them A and B. The elements are pairs of integers, right? We have a vector of pairs of integers. So elements inside will be pairs of integers. I pass in two pairs of integers, and if I want my first pair, that is for A, I want before B, then I'll return true. Otherwise, I'll return false. When should my A come before B? My A should come before B if its value per unit weight is higher than B's value per unit weight, right? So I simply return uh, a dot second divided by a dot first greater than b dot second divided by b dot first. This double is basically to convert it into floating point numbers, because in the example I discussed we had pretty nice divisible values. We will not always have that, and if I do not put double there, integer division will take place, thus giving me wrong values. So I compare value per unit weight. If A is value per unit weight is greater, this will be true. So true will get returned. Otherwise, this condition will be false. So false will be returned. And my sort function will say, okay, B needs to come before A. So that is the sorting done. And now it's just a simple while loop. While current less than weight. I've declared two variables here, if you can notice. Current is the current amount of weight I have put in my backpack, and value is the current value I have. Like value I have put in my backpack, value of the items. So this case checks if the weight of the item I'm trying to put in now is less than or equal to the amount of weight I can fit in my backpack. That means can I fit the whole item in my backpack or no? If I can, very simple, add the entire weight of the item into my current and add the entire value of the item into my current, into my value. Otherwise, then this looks a little complicated, but it's basically just seeing this W minus cur is the amount of space I have available in my backpack multiplied by items dot second. What is items dot second? That is the value. So value divided by unit weight. So double items I dot second divided by double items I dot first gives weight per unit value, correct? And value per unit weight, correct? And I have this amount of weight that I can fit in. So if I multiply the amount of weight I have left by weight, value per unit weight, I'll have the value I can get, right? So that whole long line is basically that calculation. If you want to understand it better, you can split it into two different lines, and that will probably be more readable. And then I'll simply set current equals to weight, because this case only executes when I'm inserting the last item, right? After inserting this, my backpack will be full. The while condition will stop and I'll return the value. So that is the code. So yes, does anyone have any doubts? Okay, so yeah, a lot of greedy problems are just like this. The main challenge you all will have in greedy problems will be identifying whether a given problem can be solved greedily or not. Because not every problem can be approached in this way, correct? In this, okay, in these kind of problems, they're telling you that it is a greedy problem, so you are approaching it greedily. But otherwise, you'll have to figure out, can I do this greedily or not? Because sometimes in a lot of cases you'll find out that, okay, if I just take the most greedy approach, I won't be able to do the problem that way. So the first step in all of these problems is always figuring out whether I can do it or not. A simple example I can give you is, say you had to create a sum of 15, and you were only allowed to use 10 7 5 or 3. Using 10 7 5, 10 7 5 or 3, create a sum of 12. You can add the numbers in any way. If you're using a greedy approach, what would you do? If you would say, okay, first take 10, then check, then subtract 10 from my 12, so I have 2 left. Can I make 2 from the given 3 5 7 10? No, so this is not possible. But that's obviously not true, right? You can take 3 3 3 3, like taking 3 4 times will indeed give you 12. This doesn't follow the greedy approach, but it is a valid solution. So your first step in solving a problem should always be to check if it can be solved greedily or not. So yeah, now let's move on to problem 2. It's called the job sequencing problem. Over here, it is quite similar to the first problem. We are given a, just a second. We are given an n by 3 2D array jobs describing n jobs where jobs I0 denotes the ID of the ith job, jobs I1 denotes the ID of the job I1 denotes the deadline, and jobs I2 denotes the profit associated with the ith job. So basically we are given n jobs, and we have to decide which ones should we do to get the maximum profit. So think about the greedy approach for this. What if you were in this position, you had a lot of jobs to do and some paid more than the other, each had a deadline to it. What would you do in your real life? So of course you would prioritize the job that gave you the most profit, correct? So the job that gave you the most profit, you would do at any cost. That job has to only be done, no matter if its deadline is on day 1, day 10. Exactly, yes, do the maximum profitable job. Notice in this problem, they've mentioned that each job takes 1 unit of time only to be completed. So each and every job is taking the same time, but some jobs pay more than the other jobs. So it is very obvious that you will do that job first. So you will do the you that is very obvious from the last problem also, do the most profitable job at any cost. Like, you have to only do it. But when will you do it? That is the question. You will do it always. You will do it one day before its deadline only, right? Like studying for an exam also. If you have a data structures exam tomorrow and an algorithms exam after 5 days, and you haven't started preparing for either, you won't start studying algorithms right before your data structures exams, right? You'll study your data structures, and then later you'll start worrying about doing your algorithms ka problem. So we'll do exactly the same thing over here. We'll do the jobs as close to the deadline as we can. So two things we have to notice while doing it greedily: we do the most valuable jobs, and we do the jobs as close to the deadline as possible. Let me show you a dry run for this with numerical values so you all can understand better. So over here I have four jobs. Over here, you can basically ignore the first value in every vector. It's basically saying what the job number is, really irrelevant to us. The second value is the deadline of every job: 4, 1, 1, 1. So three jobs have a deadline of 1, and values are 10, 20, 30, 40 of like the four jobs. So yeah, that's our problem, right? A lot of jobs have the same deadline. We have to decide which job we do first, and each job takes the same, like one unit of time to do. So I'll do exactly what I described. I'll sort the jobs in the descending order of profit. So 40, 30, 20, and 10. And we have the deadlines over here: 2, 2, 4, 1. I have this deadline as 2. So when will I do the job? I'll do it on the second day only, right? I'll do it as close to my deadline as possible. Can anyone take a guess on like why I am doing this? And
Bro, could you please repeat?
why do I do all of these jobs as close as the deadline, as close to its deadline as possible? Why not, for example, see, this job has a deadline of 2. Why won't I do it on the first day? Or this job has a deadline of 4. Why won't I do this on the first day?
Because if we do that, then we may miss out some other job that has to be done before.
Exactly. Suppose I did this job on day 1, then later I wouldn't be able to do this job, right? This job has a deadline of 1 only, and this job has a deadline of 4. So might as well do the job with deadline 4 as late as possible, so one can be done on its time. So basically we are trying to avoid collisions of deadlines. That's why we do them as late as possible, just like in real life. So I do what I described: take the highest profitable job, put it on the maximum deadline until I cannot perform jobs anymore. So I have a good animation for this exact test case. So let's take a look. First, we do the 40 job, we do it at day 2. Then we do the 30th job with profit 30, and that also has deadline 2. But our deadline 2 is occupied, so we do it as close as possible. So we do it on 1. And then we do the job with profit 20. We do it at deadline of 4. Actually 4 or 3 won't really matter in this case, but we need to implement an algorithm, right? So we say as close to the deadline as possible, so do it on day 4. But now notice the last job we do not really have time for. Day 1 and 2 are occupied by job ID 3 and 4, and this deadline is 1 only, so we can't do it. But it does not matter, because in doing this job we would either have to lose on the 40 profit or 30 profit, and this has a profit of only 10. So it does not make sense to do it, right? So we'll ignore it. It is fine. We are greedy. We'll do whatever benefits us the most. If that job is lost, it's lost. We got a more profitable one instead. So yeah, that is the approach we follow. Now let me just show you the implementation. Again, a custom comparator. How have I sorted this array? How have I sorted the vector? Like what am I looking for? What will I sort it on the basis of? Does anyone want to take a try? I just explained like most profitable jobs first, right?
Yes.
Yeah. So again, using a custom comparator, very similar to the first. See, this problem is almost the same as the first one, correct? Only complexity that has been added is the case of deadlines. Just a second. What is this question? We go till the job having the last deadline. Yes. So we'll create a set with the maximum deadline that of a job. So over here they've created an array, right? And they created an array of size 4. Why 4? Not randomly, because the last deadline is 4. So no jobs can be performed after 4. So we don't have to worry about the rest. So we'll create an array or a set of size of the largest or the latest deadline. Yeah, so as I was saying, we'll sort the jobs in the order of their. Okay, so the first problem was the fractional knapsack problem. It is quite similar to this problem only in that we had to take in items with maximum value in a backpack of a specific weight. So yeah, so that is quite similar to this. In that also we sorted by value divided by weight, and it's quite similar to this. Take a look at this problem, try solving it on your own. Otherwise we'll be uploading the video recording of this session very soon, so you can go through that also later. So yeah, I'm sorting the vector according to the maximum profit. I declare three variables over here: int max profit, number of jobs, max deadlines, and over here max deadline equals to. So just like someone asked, I think who would ask? Dhruv had asked, right? What is the size of the array or this set? Maximum deadline. So to find that maximum deadline, I am running a for loop to find like, okay, till what date do I have to keep a track of? Like, or what day do I have to keep a track of? I'll use a set. Actually, the thing with this problem was that it was very restrictive on the method you can use. If you use a method that is little slower, also now it will give you a time limit exceeded on 2 or 3 test cases. So that's why this set method will be used. Otherwise, if you're giving on some like other platform, you come across this problem in a little easier way also, no, you will find out that you can use a vector also, you can use an array also. But over here, I'm using a set to make it as efficient as possible. So this set is called slots. It is sorted in descending order. Like normally, if I don't put this greater int right in my sets, all the values present in my set by default are in ascending order. If I put this greater int, it's a comparator, just like I've created my custom comparator up there for sorting. This comparator tells the set to store all of its values in descending order. So yeah, over here I basically insert all of the possible slots. So for this case, I would insert 1, 2, 3, 4, because those are the four possible slots I can complete jobs in, right? And then I'll iterate over my sorted jobs array. I check if my slots dot size is equal to 0. That means I do not have any slots remaining, or my or the job that I want to do has a deadline which is smaller than the deadline that I have. I'll move on. I'll just continue because there's no case I can do it like that. Correct. So I'll find the available slot. Lower bound finds the value that is just greater than the given value. So I'm finding the deadline that is just greater than my given deadline. Like greater as in the sense closest to, like if my deadline is 4, I'll have to find 4 or 3, like that. So I'll find that deadline. I'm keeping a track of the profit, of course. And since they want us, like over here, they've asked us to return a, a vector which contains the number of jobs done and the maximum profit. So I'll keep a track of the number of profit, a number of jobs done, and at the end I'll erase that slot from my available slots, and I'll push back at the end. I'll push back the number of jobs I've done, the profit I accumulated, and I'll return my answer. And yeah, as you can see, that was a problem for today. Over here, you can see how many failed submissions because of one or two test cases. Yeah, so don't get discouraged if like your problem is if your code is not passing. This problem was very restrictive in that sense. Like yeah, over here you can see 57 test cases, 57, 59, 59, and then finally like using sets I got 60. If you want to take a look at the array approach, I can show it to you over here also. Over here it's not passing, maybe other sites will pass. So yeah, you can do this by vectors also, not over here, but maybe in an interview, if an interviewer asks you, you can do it through vectors. So yeah, those are the two problems for today. Does anyone have any doubts? Okay, so do try out the problems on your own. Try out other greedy problems. It's a very easy concept to understand. With a little bit of practice, you all will come to know how to do it, be able to implement it yourselves in no time. So yeah, I'll be sharing the solution. This video will be up on YouTube too soon. Yeah, sign up on Coding Ninjas also. We'll be having contests and we'll be giving out weekly rewards, monthly rewards. So yeah, do sign up to Coding Ninjas.
How we will get the t-shirts, of course.
I will have to speak to like the Coding Ninjas representative and my team, and we'll get back to you soon. Like, I'm not really sure if we'll be on what the details of it are, but just like drop a message on the group, and I'll get back to you. Yeah, so I'll be ending the meeting. Thank you all for attending.